now begin to take a look at two physical processes that are quite similar to each other, explosions and collisions. As we'll see later on in this unit, collisions in particular are extremely important in physics, but for now the two processes are very similar to each other physically. I'm going to simulate both of these processes by using these carts. Each of these carts, for example, has an elastic band that can be compressed. And I'm going to first of all simulate an explosion, what's called a one-dimensional explosion, by setting up the following. I'm going to take the two carts and initially compress them together like so, and then release the two carts from rest, and they explode apart like this. I could also represent a collision by taking the two carts and simply colliding them together like so. As we'll see, the two processes are very similar to each other. The whole time that these processes occur, for simplicity, we'll picture it all happening on a horizontal frictionless surface. If that's the case, then the sum of the external forces acting on the system as a whole is equal to 0, and then therefore the momentum of the system is conserved. Now, I've been talking about momentum and its conservation throughout this unit thus far, but I've never done any calculations associated with momentum, nor have we seen as of yet a conservation equation associated with momentum. That's what we're going to derive here, first of all, by setting up a situation involving these carts. In order to do so, I'll do so by picturing a collision. So we have explosions and collisions. And as I said, for simplicity, we'll assume that the processes take place, or the processes occur, on a horizontal frictionless surface. This then means that the sum of the external forces acting on the system as a whole is equal to 0. And as I said, let's picture a collision. There's a total amount of momentum before the collision, and there's a total amount of momentum after the collision. The two quantities are equal to each other because the total momentum of the system is a constant. It's a conserved quantity. So here's then how we begin to write this out. So let's picture a collision. Okay, and then before the collision, we have the two carts. We have the first cart, we'll say, moving in this direction like so with an initial momentum I'm going to call P1 naught. Okay, and then we've got the second cart like so, moving, say, in this direction. Its initial momentum is P2 naught. The total momentum of the system is the momentum of the center of mass. So the momentum of the center of mass is equal to P1 naught plus P2 naught, like so. Okay, and then the collision takes place. And then after the collision, the carts bounce off of each other in some manner, as we saw. So now, after the collision, and then we've got this cart now at a final momentum, we'll call it P1 final. And then we've got this second cart like so. This guy has a final momentum, we'll say P2 final. The momentum of the center of mass, however, is exactly the same as it was before, because once again, the sum of the external forces acting on the system is equal to 0. Therefore, the total quantity of motion, the momentum, is a conserved quantity. So after the collision takes place, the momentum of the center of mass is the momentum of number 1 plus the momentum of number 2. That is P1 final plus P2 final. Therefore, the change in the momentum of the center of mass from before to after the collision is equal to 0. This then allows us to come up with a conservation equation. Here's then how we write that. Okay, so take one of the expressions and subtract it from the other. So then therefore the change in the momentum of the center of mass is equal to the change in momentum of cart number 1 plus the change in momentum of cart number 2. Well, once again, this quantity here on the left-hand side of the expression is 0 because the total momentum of the system is a constant. It's a conserved quantity. And then, therefore, we end up with the following conservation equation. This expression right here. Change in momentum of number 1 from before to after the explosion or the collision, plus the change in momentum of number 2 from before to after the explosion or collision is equal to 0. The beauty of using this expression is that all that we really have to do is fill in all the respective values of mv, that is momentum, to solve for whatever it is that we're looking for. And we don't even have to worry about the center of mass itself because the change in the momentum of the center of mass is equal to 0. So let's immediately go ahead now and take a look at a simple situation involving an explosion. We'll take a look at a one-dimensional explosion first, and then a little bit later on we'll take a look at what is called a two-dimensional explosion. So let's go ahead and erase the board and then access the first lecture example. Okay, so this first lecture example, go ahead and copy it down into your notes, represents a one-dimensional explosion. Okay, let me go ahead and read the problem to you, and I'll also demonstrate it here as we work our way through the example. Okay, two carts explode apart in one dimension. The velocity of the first cart after the explosion is 1 meter per second. If the carts have the same mass in part A of the problem, what's the velocity of the second cart? And then we'll see what happens in part B if we change one of the masses of the carts. Okay, so we're going to set the problem up in the following way. Okay, here are our two carts. We'll call them M1 and M2 here initially. In part A of the problem, those two quantities will be equal to each other. Both of the objects are initially at rest, and then they explode apart. Okay, let's say that number 2, like so, explodes off in this direction with a V2 final that's given to us. We'll say that this is the 1 meter per second that's given in the problem. But then we have M1. Now, presumably, M1 explodes off in the opposite direction, like so, with an unknown final velocity V1 final. If, in fact, it does explode to the left-hand side, when we do solve for V1 final, it should be a negative number. Well, let's see. And now we set up our conservation equation. So change in momentum of number 1 plus change in momentum of number 2 is equal to 0. This is a one-dimensional problem, so I can go ahead and drop the vector symbol for that reason. And now let's just start filling in our terms of final minus initial of mass times velocity. So first of all, for cart number 1, its final momentum after the explosion is M1 V1 final. Okay, minus its initial momentum prior to the explosion, which is equal to 0, because keep in mind that both of the carts are initially at rest. And then we've got cart number 2. So after the explosion, its final momentum is M2 V2 final. And then minus the initial, which is once again 0, because that cart begins at rest. And now we just solve for V1 final. So to solve for V1 final, move this term here to the other side and it becomes negative. Like so. And then we'll go ahead and come up with our equation now that we'll use for part A and part B of the problem by taking the mass M1 and dividing it to the other side. So then therefore I end up with the following expression for V1 final. Like so. And notice the negative sign here. The negative sign, of course, means that the V1 final vector is going to be the opposite direction of the V2 final vector. And now let's go ahead and apply this then, first of all, to part A of the problem. Okay, so in part A of the problem, it says that the carts have the same mass. So then therefore M1 is equal to M2. If the masses are equal to each other, they cancel out. And then therefore V1 final is equal to negative V2 final, and as you probably guessed, the answer is negative 1 meter per second. So then therefore, if the carts have the same mass, they explode off into opposite directions with the same speed. So here's then how we can demonstrate that. These carts here have approximately the same mass. There is a little bit of friction here, of course, associated with the table, but let's ignore that. And then we begin in the following manner. The carts are initially at rest like so, and they explode apart. This guy here explodes off in that direction at 1 meter per second. This guy here explodes off in that direction at 1 meter per second. Think of it this way. What is happening to the center of mass the whole time in this problem? Well, because these carts have the same mass, the center of mass is right here, directly in between them. The velocity of the center of mass is 0 to begin with, and it's 0 the whole time. So then therefore the MV of this cart in this direction has to exactly cancel out with the MV of this cart in the opposite direction. So 1 times 1, say, for that cart in that direction is being canceled out by 1 times 1 by this cart in this direction for part A of the problem. Okay, now let's change it up a little bit for part B. Let me move my file. Okay, so now it says, what if the second cart, this guy here, is twice as massive as the first? So let's go ahead and double this guy's mass by placing this object here, and then once again this cart here explodes off in that direction at 1 meter per second. What do you suppose the velocity of this cart is going to be in the opposite direction? Well, let's go ahead and calculate it out first. Okay, so now here's part B of the problem. Now we're given that the mass of the second cart is twice that of the first, like so. So then therefore, let's go into this expression here and set m2 equal to 2 times m1. So then therefore, when I do, like so, the m1's now cancel out, and then therefore, the velocity of the second cart is going to be negative 2 times 1, or negative 2 meters per second. So this guy here is going to have to explode off in that direction with twice the speed of this guy here in that direction. So if this guy is 2 kilograms and this guy is 1 kilogram, for example, this guy, by definition, explodes off that way at 1 meter per second. So think of this then, therefore, as 2 times 1 in that direction. Therefore, this guy here has to be 1 times 2 in that direction, such that the total is equal to 0 the whole time. And that then basically looks like this. Notice that the speed of this object here after the explosion was basically twice that of this one here. And then in part C of the problem to finish, it says, is it possible for an object to explode into 2 pieces into a plane? In other words, for part C of the example, what we're being asked to show is that essentially, why is this a one-dimensional explosion? So think of it like this. Let's say that we once again have these 2 carts and they explode off from each other. Let's say that by definition, this cart here explodes along the positive x-axis. Is it therefore possible, after I let go of the objects, for this cart here, for example, to do something like this, move along the y-axis in some manner? And the answer to that question, of course, is no. And the reason for that is because if this guy explodes off in the positive x-axis in this direction with some mv, this guy has to explode off in the negative x-axis with an equal amount of mv. So the mv in that direction has to be exactly canceled out by the mv of this object in that direction. If this object here was to explode into the y-axis in some manner like so, that momentum would have come out of nowhere. It would have been created, and it's not being canceled out by this object here. The only way in which this object could explode into the y direction of some sort is if there is an external force, such as myself present, that is being able to do something like this. But if I'm not there, then this truly is a one-dimensional explosion like so, as is described. The mv that way is being exactly canceled out by the mv in that direction. Okay, and then in the next video, we'll follow up by taking a look at a 2-dimensional example.